Hey everyone, I am Kehashit. Today I am going to explain the concept of radiation and we are going to solve a few problems based on radiation. So, the topic is radiation. So, before understanding anything about radiation, let us discuss something about a black body. What do you mean by a black body? A black body is a perfect absorber and perfect emitter of all the radiations. So if this, suppose say this is a black body, then this a black body is such a body which is able to absorb all the radiations present and is also emitting all the radiations that are present. This is a black body. Now if I am saying the basic formula that is given to calculate the energy here in the radiations is energy is equals to dq, change in the heat, by dt, change in the time, into area. This is the basic fundamental formula that we are going to use it here. And the actual definition of energy in this concept is, so reflecting, I guess, yeah, energy is nothing but energy is directly proportional to temperature power 4 at a given, for a given unit area, in a unit second, per unit time, I can say. So energy is nothing but t power 4, t power 4 times per unit area per unit time. This is E is directly proportional to t power 4. This is the first definition that is given for energy. Then what I am doing is, place of sigma in the place of proportionality symbol, I am replacing it by sigma symbol. Yes, and then this is the formula for energy. Here sigma is called Stephen's constant. Stephen's constant, and as it's a constant we have a fixed value for this, 5.67 10 to the power of minus 8 watt per meter square Kelvin power 4. We will see how we got these units, watt meter square Kelvin power 4. We will see how we got that in a couple of minutes. Now, so in the place of E, I am writing this expansion. So sigma t power 4. In the place of dq by dt, we know that dq by dt is nothing but power. Power is nothing but change in heat by change in time. So in the place of dq by dt, I am writing power by area. Hence area I am transposing this side, so it becomes power is equals to sigma t power 4 by t power 4 into area. And this area depends for a sphere, for a cube, and for a cylinder. So different areas we will be using for a sphere, cube, and a cylinder. This is the another basic important formula that we be using. Okay, so this sigma constant, whatever is this Stephen's constant, this value we must remember, because chances are there that they may not give the value for in the question, so better to remember the value. Now let us see how we got this watt per meter square Kelvin power 4. I am taking this equation I am taking here. So P is equals to sigma t power 4 by area. Now I wanted the units for sigma. Keep sigma here, transpose everything that side. So you get P by T power 4 area is equals to sigma. Units of power is watt, units of area is meter square, temperature is Kelvin power 4. Hence, this can also be written as watt per meter square. I can write Kelvin power 4. By seeing the units, we must be in a position to identify what is given to us. They are giving watts. It means that they have given us the power. They are giving us watt meter square Kelvin power 4. It means that they have given the Stephen's constant or sigma value 5.67 10 to the power of minus 8. So these are the these are the few basic points that we will be using to solve any problem. Okay, and now I will be solving few set of problems, and of course there are some more some more concepts that are to be covered. So when we are doing those questions, when we are facing those concepts, then I will be explaining that concept also, how to deal. So let us see the first question in the radiation. Okay, so this is the question given to us. The ratio of intensities at a distances of r and 3r from a spherical source will be, and they have given us the options. So if you wanted to try this question, you may pause the video and you may try this question. So with this problem I am going to use this relation. First of all, what is the meaning of intensity? When we take power by area, it is equal to intensity. Power by area is equals to intensity. Now the ratio of the distances, the ratio of the intensity at the distances of r and 3r from the spherical source r. So we have a formula for this. I didn't discuss this. So what is the formula is I is equal to, or power radiated per unit area. They didn't give per unit area, so we are assuming per sphere is nothing but r square sigma T power 4 by d square. This is the formula. I can say intensity, or I can say power by area. This is the basic formula that we should use. So whenever we see the problem, we should get the idea of which formula to use, then we can proceed. Now this is the relation that we got. Now what I am doing is, this said spherical source I is equal to, okay, so what I am doing here is r square sigma T power 4 by d square. So as it's a spherical source, I can imagine that temperature is constant because it's coming from a spherical source, right? They didn't give anything about this temperature, so I'm assuming or I'm ignoring this temperature for a while, and sigma can be constant. Yes, so here can I say that radius and distance share inverse proportion? Can I say that radius and distance share inverse proportion? So what I am doing is r square by d square. This is the relation that we got at last. This is nothing but intensity. Okay, so r square by d square, which is nothing but, let me expand it, radius square by distance square. This distance is from the source they have given. Now see here, they said distances are r and 3r. So can I say that I am imagining radius as 3r and the distance as r. Okay, so the image is like this. This is a spherical spherical object from this at this distance. This is r, this is 3r. Two objects are situated. So now here 3r by r, square here, square here. 3r square means it will become 9r square by r square. Yes, r square cancel. So I get intensity as 9:1 ratio. So the ratio of the intensities here is 9:1. So in the given options, if we look at, this is the correct option. 9:1 is the correct option. Yes. So now let us move to the second question. So the second question that is given to us is, I will read the question. The question says, an incandescent bulb has tungsten filament that is heated to a temperature of 3 into 10 to the power of 3 Kelvin when current passes through it. Then the surface area is approximately 10 to the power of minus 4 meters square. They said here approximately, so maybe chance it is there, we may get the answer approximately, we may get the answer, not so near, we should approximate, we should round estimate it. Okay, then emissivity is 0.32, the power radiated is. So for this formula, for this sum, I will introduce a new formula for us. So whenever they are giving emissivity, whenever we are taking a black body has its emissivity as 1. So whenever I have written the formula, P is equal to area sigma T power 4, I didn't write anything about emissivity because we are discussing about the black body. So in a black body, the emissivity is always 1. The emissivity is always 1. Then what about the ordinary bodies? Ordinary bodies, this is for a black body. For ordinary bodies, if we are talking, then the emissivity lies within 0 to 1. It lies within 0 to 1. It cannot be negative, it cannot be more than 1. 1 is the maximum emissivity that is given to the black body. Okay, so that's the reason why I didn't write here emissivity, because for a black body emissivity is 1. We know this. Now they have given us emissivity, so what we are doing, we are changing the formula. What is the basic formula? Power is equal to area sigma T power 4. So as they have given us the emissivity, we are even including E here. Okay, so yes, now nothing is there, this is the formula. If you get this formula, then it is all the simplification that is there to deal with us. Now area they have given as 10 to the power of minus 4. Okay, sigma is, they didn't give the value, but we know it, 5.67 10 to the power of minus 8. Okay, then temperature is given 3 into 10 to the power of 3 whole power 4. This is the temperature given. Then into emissivity is given as 0.32. This is the emissivity given to us. Now simplification, that's it. 10 to the power of minus 4, 5, 6, 7, let me say 5.67 10 to the power of minus 8, 4, 3 power 4 is 81, exponent law, a power m bracket of bm, or we have this, no, right, a something power b or something power m to the power of n, we do a into mn. This is the basic that I am using here. So 3 10 to the power of 3 whole power 4, 4 3s are 12, 10 to the power of 12, and 32 10 to the power of minus 2. Now see here, minus 4 minus 8 minus 12 plus 12 cancel. That's it. This cancellation technique we should be able to understand for easy calculation. So now what is left with us? 5.67, 81, 32, 10 to the power of minus 2. So when you simplify this answer, you get something around 146, 96.64 10 to the power of minus 2. This value I got after multiplying it. So yes, I am not multiplying here because it may take some time, but you people, you should be in a position to multiply these all things. You multiply 5.67 into 81 into 32, you will get this answer, and then 10 to the power of minus 2 means 2 point this side, 146.96, you will get it. This is what? Power, watt. This can be approximately equalized to 150. Why 150? They said approximately the area, surface area is approximately, so power also approximately, this can be rounded off to 150. So 150 is our answer. Let us look at question number 3 now. Yes, so what does question number 3 says is, the rate of emission of a black body at temperature 27 degrees centigrade, this is the keyword, is even. If its temperature is increased to 327 degrees centigrade, then the rate of emission is E2. For 27 degrees centigrade, the emissivity, the emission is even. When temperature is increased to 327 degrees, then the emission is becoming E2. Now they are asking the relation between E1 and E2. Now see here, the basic formula is same again. E is equals to, here I am using E is equals to sigma T power 4. We know this, right? E is equals to sigma T power 4. This you know, you can solve it. They are asking E1 is to E2. So can I say E1 is sigma T power 4 1, E2 is sigma T 2 power 4, can I say? Now just they are asking us the ratio. So E1 by E2 is equals to sigma T1 power 4 by sigma T2 power 4. Now sigma cannot be sigma 1 sigma 2 because sigma is a constant, so sigma gets cancelled here. Now what's happening? They are asking E1 by E2 is equal to, now see, here comes another twist. The temperature is given in Celsius, the temperature should be given in kelvins, because when we wrote the relation, I said is we got the Stephen's constant as watt meter square Kelvin power 4, Kelvin power 4. So that's why units cannot be in centigrade, you have to convert them into Kelvin. So we know that you should add 273 because 1 centigrade is equal to k plus 273. Sorry, k is equals to 273 plus c. This relation you use. So when you use this relation, okay, k is equals to 273 plus c, what you get here? 273 plus 27 gives you 27, 273, 300. So T1 I am writing 300. 327, 273 gives us 600. Yes, 600 power 4, power 4. I can write 300 by 600 whole power 4. Yes, power is for here 4, here 4, so whole power 4. 0 0 0 0 cancel, 3 1s are 3 2s are. Okay, now see, this is nothing but E1 by E2. E1 by E2 is equals to 1 power 4 is 1, 2 power 4, 2 2s are 4, 2 2s are 4, 4 4s are 16. So E1, sorry, yeah, E2 is equals to E1 or 16 or 16 times E1. So see here, this is the relation that we got. E2 is equals to 16 times E1. Yes. Okay, coming to the fourth question now. What does fourth question says? The radiation emitted by star A per second is 1000 times that of sun. Okay, then the surface temperature of sun and star is 6000 Kelvin and 2000 Kelvin respectively. Then the ratio of radii of star A to the sun is, they are asking. So what formula I am using here is E is equal to just a second, E is equals to E is equals to sigma A T power 4. This is the equation that I am going to use. Now emission of sun is X. They said they didn't give this. They said that the radiation emitted by star A is 1000 times that of sun. If sun radiation is x, then stars would be 1000 times x. This relation you should get first. Then now substitute here. I am taking ES U for sun. They said they're asking star and sun, so let us better take in this format. First E star by E sun. They're asking that's the relation only, which means that sigma A T power 4 sigma A T2 T1 power 4, sorry, A2 A1 T1 power 4. Sigma sigma cancel, constants. Okay, star is 1000x, sun is x, because we got this from the relation. Yes. Now next what I am doing here is area. They said sphere, so area of a sphere is 4 pi r square. Area of sphere is 4 pi r square. Okay, now in the place of area I am writing 4 pi r square, temperature power 4 4 pi r square r2, better say t2 power 4. Nothing to worry about these pi blah blah blah, because those both are same in numerator denominator. Yes, so we should know that when they are given as area we should take radius square. Okay, you are not knowing the formula for the area volume, no worries. If they are giving volume r cube, they are giving area, then it's r square. Now see here, r1 1000x, so I will better solve it here. 1000x by x is equals to r1 square, sorry, r1 square by r2 square into t1 square. What is t1 square given to us? T1 is nothing but of the star, it is 2000 by 6000, 4 double triple zeros cancel, 2 3s are r. What is r given to us? We should find this only, right? r1 square r2 square. Can I write 1 by 81 is equals to 1000, x cancel, no? Yes. Now see here, keep r1 r2 like this only, because r1 I am imagining as for star and then for sun. So 1000 into 81 by 1 will give you r1 square r2 whole square, I am saying. Okay, next 81 000 by 1 is equals to r1 by r2 whole square. Yes, bring the square this side, becomes whole root 81 000 only. Okay, 000 by 1 whole square. Okay, so now is equals to r1 by r2. Can I say 9 9s are 81, 90 can I say, or 900? One more zero should be extra here. 900 81, 4 zeros. Oh sorry, question mistake, I'm so sorry. Question says it's 10,000 times, not 1000, 10,000 times. I'm so sorry. Question says ones, tens, hundreds, thousands, 10,000s. 10,000 times. No, it's not 1000, it's 10,000 times. So now if they are saying 10,000, just change, small change, extra 0, extra 0, extra 0, extra 0, extra 0. You get 900 by 1. Okay, 900 by 1 is equals to r1 by r2. Therefore, radius of star to radius of sun is 900 is to 1. So option C is your correct option. Okay, now, so I would like to stop here the session, and we will discuss few more problems based on radiation, and then after that we will check for problems based on Wien's displacement law, and then after that we will see for the Newton's cooling laws also. So you may take the screenshot of this question and you may try it. So mainly the questions that we came across is mostly are of the ratio types. So whenever they are giving ratio types, we should be very careful. Are they asking this by this or this by this? So few things must be kept in mind when we are solving ratio problems. Okay, then I hope you all have enjoyed today's class. Thank you so much.